In this example, we were given two mechanisms and we were asked to determine which was acceptable. They both ended up being acceptable mechanisms in that they simplify to the desired balanced equation, and then the rate law, based on the molecularity of the slowest step in the mechanism, matched what we experienced in the lab, the experimental rate law. Our overall reaction rate can't be any faster than that of the slowest step in the mechanism. So here's one way that we could see a mechanism question. Is this given mechanism acceptable? We will never be asked to write a mechanism. These are really complicated and would really take a lot of prior knowledge of these reactions and a lot of lab experimentation, and they're just really hard to design and study. And so we will not be asked to come up with our own mechanism. We would be given a mechanism and asked if it is acceptable. Now, the other thing they could ask me is, let's say I'm given a mechanism, maybe it's mechanism 2, and maybe they don't give me the experimental rate law. Well, then they could say, okay, if mechanism 2 is an acceptable mechanism for this particular reaction, what would be the expected experimental rate law? If I were to run this in the lab, what would be the expected experimental rate law? And then we would say, oh, well, if this is an acceptable mechanism, then if I write a rate law based on the molecularity of the slowest step, then this should be what I would experience in the lab. That if I doubled the concentration of the nitrogen dioxide, it would double the rate. And also, if I doubled the concentration of fluorine, it would double the rate. That in the lab, I should find the reaction being first order with respect to each reactant. So I want to show you another example. There's a couple things that I wanted to highlight with something like this. So number one, it is asking just that. It gives us a proposed mechanism for this chemical reaction. It is shown above. Which of the following rate laws is consistent with this mechanism? So it should, number one, balance or simplify to the desired balanced equation. Should we check? Should we just make sure? If I cancel anything that's the same on both sides, it should simplify to the desired balanced equation. So I could have intermediates. Intermediates are particles that are formed in an early step and then they are consumed in a later step. Let's see, I have another intermediate. Here's some fluorine atoms that are formed and consumed. So once I cancel anything that's the same on both sides, it could be an intermediate or a catalyst, then I should simplify to the desired equation. And we do. I would have a total of 2 nitrogen dioxide on the reactant side. I'd have the 1 fluorine, and I would have the 2 NO2F on the product side. Okay, so yeah, step 1 is great. Simplifies to the desired balanced equation. And now they're kind of saying that if this were an acceptable mechanism, which of these rate laws should be consistent? Which of these rate laws should I experience if I go in the lab? Okay, so here's what I want to show you about this mechanism. It's a little bit different than the mechanisms that we previously looked at, even though they're all for the same balanced equation. You can have multiple acceptable mechanisms, and then it just becomes a matter of studying these things like crazy in the lab to find, well, what really were the intermediates, or what was the catalyst? Do I think that in this case I have a slow step at step 2 of the mechanism? Or here do I think maybe step 1 in the mechanism is slow? Is it more likely that the reaction runs in maybe 2 steps? Or is it more likely that it runs in 4 steps? I mean, eventually we want to try to keep our mechanisms relatively simple, because if I think about this on a particle level, the more steps I have to my mechanism, the more collisions that I'm relying on happening all effectively in order to get me from the reactants to the products. Now, we will never have to say then which mechanism is best. We would just be asked which mechanism is acceptable. And so here might be 3 acceptable mechanisms for the same reaction. Now, what's a little bit different about this one is that in step 1, you've got a double-sided arrow. And it's definitely something that we're going to focus more time on in the next couple units. Here it's just listed as fast. Sometimes it might say fast equilibrium. Sometimes it might say that it's a fast equilibrium. This is a reversible reaction where you have a double-sided arrow, and it's definitely something that we're going to highlight over the next month or so. What are reversible reactions? And they are just what you would expect. It's a reaction that starts with reactants, it forms products, but then those products can go back to the reactants, and it flip-flops all day long between reactants and products, where really they both exist simultaneously, the reactants and the products, because I'm always flip-flopping. Some of the particles are the reactants, some of the particles are the products. So you've got all components present. It's not like some of these other reactions that have a one-sided arrow where you have reactants, they form products, the reaction goes to completion and eventually stops. Here, when I form products, then they go back to the reactants and flip-flop all day long. It's reversible. Okay, so here's another problem. The slow step is now step 2. And if I were to write a rate law based on the molecularity of the slow step, we just said that this guy here is an intermediate. This guy was an intermediate. It was formed in step 1, but now it would be consumed in step 2. So initially, I had crossed these things off. I had crossed off my intermediates, and then fluorine was another intermediate. I'd crossed those off. Intermediates cannot appear in an acceptable rate law. They're not part of the desired balanced equation. And so here's what we got to do with this one. When you have an early step that is an equilibrium step, well, it really means that this intermediate is equivalent to all of this, that they both are formed and consumed and present at the same time. And so I don't want an intermediate to show up in my rate law, because obviously that intermediate is not something that I'm going to study in the lab. That's not something I can control in a lab setting. So what we're going to do is make a substitution. I'm going to take what's opposite the intermediate in step 1 because it's reversible. So both reactants and products are present at the same time. So I'm going to take these reactants from step 1 and substitute that in for my intermediate in step 2. Now you can only do this when your early step is reversible, where it's got that double-sided arrow. And so then I'm going to take what's opposite my intermediate, because they're equivalent, they're reversible in step 1, and I'll substitute that in for the intermediate in step 2. And now look what we're going to have in step 2. If I substitute in the equivalent to the intermediate from step 1, and if I write a rate law, then I would have R equals K, my constant, and then I would have the concentration of NO2. There's one of them to the first, and F2, there's one of them to the first. So it's this equivalent to the intermediate that I'm going to substitute in replacement of the intermediate in step 2. And then bingo, here it is. And that was the experimental rate law that was given in the previous example. So I wanted to show you one that's got this reversible fast step. And so when it's reversible, and I don't want an intermediate to be in my slow step, you can take what's opposite the intermediate in step 1 and substitute that in for the intermediate in my slow step 2.